So let's look at this exercise 1.1.7. Compute the simplicial homology for this tetrahedron. Recall the definition of this simplicial homology. Firstly, we define what are those. What is this homology? What is this chain complex? It's chain complex by defining firstly what are those CK. So C0 in our case is a free R module whose basis is given by vertices. Respectively, C1 is a free R module whose basis is given by edges, and C2 is a free R module whose basis is given by faces. So one important thing is we have to fix an order at the beginning for the vertices. So let's fix V0, V1, V2, V3. So the order is the increasing of the index integer 0, 1, 2, 3. By doing this, so geometrically we gave orientation for all those edges, and also for those triangles, because so the orientation comes from the vertices, nothing to do. You don't have to care about other things, just comes from the vertices. For example, if you look at the face 1, then you could say this orientation should be anti-clockwise. The reason is that it should be the direction that is the same as the increasing of the index. So it's V0, V1, V2. So it's this anti-clockwise. Similar reason for F2, it should be V0, V1, V3. So like this. And then for V3, correspondingly it should be V1, V2, V3, and so clockwise. And for V4, clockwise. Okay, it's totally defined. This orientation is totally determined by this fixed order at the beginning. And then important thing is this differential map. This differential map, the formula is given to be if you if you're acting on let's say V0, Vn. So here this is really this is abstract formula, which means V0 means the first position entry, Vn is n+1's position entry. I will explain what that means. And so this formula is given by summation -1 to the power I, and then you remove this Vi from your vertices. This gave you, so this is n-dimensional, this will be a -1 dimensional simplex. So in practical, what does this formula mean? I mean, there is one confusion. For example, let's apply this differential to V0, V1, V2. By formula, I should tell you that this is first remove V0, which means remove the first position, keep it positive, then remove the second position V1, keep it negative, then remove the last entry, keep it positive again. And then when you apply again d over this, because we know that d squared should be 0. When again applying it, do not put the formula as if this is I, this is I equals 1, I equals, I mean, you should not say that I'm going to use -1 to the power I times remove Vi plus -1 to the power the index of the second entry, and then remove V1. It is not this. What it really means is look at this V1, V2, again your formula tells you that positive sign remove the first entry and negative sign remove the second entry. You see, if you understand the formula differently, there will be different by a sign that will not equal 0. The correct one is always, the formula is telling you that it's always interchanging of the sign, positive minus, plus minus, plus minus. No matter what precise your index integer is, the important thing is its position, not precise number, precise integer. Okay, so let's come back to this chain complex. So fix a basis, and then you got a matrix to describe it. Okay, so one important thing is that if the coefficient R is a field, then this is the computation will be very easy, because this will be co-chain complex vector spaces. So to compute the homology group, what you really care about is just the dimension of the kernel, dimension of the image, and then the dimension itself determines what is that homology group. It's always a vector space. The homology group would be a quotient vector space by subvector space, always vector space. But unfortunately, this is arbitrary ring R. Of course, integral domain. That's how you define a basis over ring R. This makes the computation slightly more complicated, but also there will be better phenomena appears. For example, you could possibly have torsion in your Abelian groups, so which means your Abelian group will not guaranteed to be free R modules anymore. It will always be R module, but it could be R module with torsion. Understand? For example, if you're talking about R equals Z, then there are examples I will mention later whose homology group is the quotient by, for example, integer 2. And so, but it doesn't stop us to writing this matrix representation for the differential d1, d2. How do you do this? This is just very similar as last exercise 1.1.6 for the graph, the homology associated, which basically, for example, your d1 maps from an edge to vertices, right? So for example, how is E1 mapped to? E1 is mapped to V1 minus V0. V1 minus V0. So you could read it quickly from picture, which means the endpoint minus the starting point. Okay, and so this is just telling you that the matrix should be the position corresponding to 1, put it 1, the position corresponding to V0, put it minus 1. This is how this matrix works. And when you apply this matrix on arbitrary vector x1 until x6 as a coordinate, of your free module, then you will see that the image is exactly, you just and the image of E1 up to multiplication by the scalar x1, because, so what I mean, let me write slightly more information. You got this, your D1 is 4 times 6 matrix, and then when you multiply by x, recall this is totally linear algebra. What you do is, let's call this first column A1, second column A2, and sixth column A6. By the rule of matrix multiplication, this could in particular be written as x1 of the first column plus x2 of the second column until x6 of the sixth column. Right, so why do I mention this? It means that this map is totally a linear combination of column vectors of this matrix D1, which means it is totally a linear combination of the image of E1 plus image of E2 plus image of E6 under this differential, right? Okay, so once we got this, then what left is just computation. As I said, if you are working with coefficient that are fields, then this is totally trivial. I don't see trivial, then totally determined by the dimension. You just compute the kernel and the image on each position. You just compute the dimension. For example, if you want to compute what is H0, so H0 should be the kernel of D0, which is totally this C0 quotient by image of D1. So if the coefficient is a field, then you just, for example, R equals Q or real number, then you just quotient R4 by R, the dimension of the image of D1. The dimension of D1 will be determined by the rank of this matrix, right? In that case, you compute and you just do elementary row operation. You determine what is the rank of this D1. You will see that the rank of this D1 is 3, and so tells you that this H0 should be one-dimensional R vector space. I'm talking about R being a field. And when you stop H0 and just do the same for H1 and H2, because given a matrix, you know what is the dimension of the rank and you know what is the dimension of the kernel, because the rank plus the dimension of the kernel equals the dimension of the vector space your matrix acting over, right? But unfortunately, as I said, we are not really in the case of field being the coefficient being a field. Rather, this coefficient is just a ring R. But in this case, what requires more to do is just to compute precisely what is your image, which means you have to take care of what is the spanning set of your image, which means which are the linear independent vectors that generate your image, and then you have to compute correspondingly which are the linear independent vectors that is in your kernel, and then you really have to compare this image and the kernel. You cannot say they're the same dimension, then you just quotient as you do for vector space. You cannot. For just take an easy example. If it happened that your kernel of the 1 is generated by the vector v, and you notice that your image of D2 actually is the span of 2v, and then what should be your conclusion? Your conclusion would not be that they are all dimension 1 and so the homology group H1 should be isomorphic to 0. Rather, it will be that imagine your R is Z. In this case, it will tell you that it's totally example. I mean, imagine this is a situation. It totally tell you that H1 should isomorphic to the quotient by 2. That's what I mentioned. The torsion phenomenon could appear. Okay. Fortunately, you compute this example. You just do those operations you legally do. You could do some elementary operation or column operation, because as I said, for example, when you do elementary column operations, what I'm really doing, I'm just doing linear combination of the image of E1, E2, E3, which is legal, right? Could always do that because it doesn't hurt my image. My image is the span of the column vectors. It makes totally sense. I do elementary column operation. It doesn't change anything, which means finally when I got these three linearly independent vectors, it really means that these three vectors spans my image. This three vector corresponds to the simplices with 0 minus v1, v1 minus v2, and v2 minus v3. And corresponding to C0, you could find a basis which is v0, v0 minus v1, v1 minus v2, v2 minus v3. And this have perfect sense to do a quotient. And it is really, in this case, that the quotient is 0, not only because you are kind of comparing their dimension, but really because this subspace as subspace of C0, when you indeed do the quotient, it is left with a free homology we see generated by V0 actually. Right? You need something more precise here. Similarly, if you want to compute H1, I also did some computation. You cannot just argue by dimension. So what you really have to do, you have to compute what is the kernel and find the basis of it, and then compute with the image of D2 and find the basis of it, and then compare this two sets of bases and discuss what is exactly the quotient. For example, the image of D2 will be again the linear combination of the column vectors. Here is the image, so each column corresponds to the image of phase 1, phase 2, phase 3, phase 4 under the differential map. And when you do linear combinations for the columns, you know that you do the column elementary column operations, you know that you're just doing linear combination of those faces and then map it through D2. And so finally we see that, okay, so the image of D2 actually is spanned by these three linear independent vectors. And then you could compute what is kernel of D1. Kernel of D1 is equivalent to solving this linear system, but one thing you should be careful is that you could not really do that for as you do for vector spaces. You could not, it's not really legal to multiply by whatever real coefficient you want, because for example you could divide by 2 when your coefficient is q, but if your coefficient is z, it's illegal to really divide by 2, right? So just keep track of which operations are you legally to do. So I'm doing elementary operation. Of course I could still minus a row by another row. It's just linear combination. It doesn't change. Yeah, okay, so we're solving this homogeneous linear system in some sense. Okay, we're trying to find what is the vector, what are the scalars that solve this homogeneous linear system. We're trying to find a basis for the kernel of D1, right? And so finally you find the kernel of your D1 is the span of these three vectors, and you compare with it and you see indeed they are the same. After this tells you H1 is 0. Okay, and so I left H2 for you to check by yourself. So what is left to do is just H2. Still what we have to do is just check where is the kernel of D2. And in that case, what you have to show is that the kernel of D2 has it's generated by one vector. Okay. Yeah. So if you just look at this matrix, if the coefficient is filled, then this is again very easy because you already see the rank of this matrix is 3. And so this space is R4. So as I said, if I'm talking about field, then this means this is 4-dimensional vector space. There you have linear operation, linear transformation rate whose rank is 3, and so the kernel would be 1. But in this case, not necessarily a field coefficient. You could, I would say this argument still works actually. It still works. but it still works here, but take care in general case.